Hi guys, today I'm going to be going over FRQ number 2 of the AP Physics 1 2026 exam. And all this text is pretty much useless except for this last part where it tells us the suggested time you should spend on each question, and it tells us that we should spend about 30 minutes on question 2. And this could help on the AP exam if you're trying to time yourself. Okay, and by the way, this is version J because they didn't release the other versions, but there were 3 other versions. So if you took this exam, you probably would, some of you did not see this question, but the majority I'm pretty sure got version J. So question 2 tells us that there are two small disks R and S, and they're on a straight horizontal track. At time t equals 0, disk R of mass m0 is located at position x equals 0, and it's initially moving speed v0 in the positive x direction, which is to the right, as it shows in the figure later on. Disk S is of mass 3 m0, so it's 3 times, and it is initially at rest, so its velocity and it shows 0. And frictional forces are negligible. At t equals t1, the disks collide immediately after the collision. Disk R speed is reduced to 1 over 2 v0 in the negative x direction. This is very important to realize, which is something I did not notice when I was taking the exam. But yeah, it says negative x direction, so it's going to be to the left, which is important. So, and then this diagram just shows you the whole thing at t equals 0. So this is t equals 0. It will have disk R, m0, v0 to the right, and then disk 3 is 3m, but it's at rest, and the positive direction is to the right. So, part A tells us that the momentum vector diagram represents the momentum of disk R and disk S. So, the momentum at t equals 0, we had disk R because it was moving. It had a momentum of technically mv, m0, v0, and it's 4 ticks. And disk S is 0. So it might be important to note that the total momentum was 4 tick marks. So then what does it want us to do? It says draw arrows on figure 3 to represent the momentum vectors of disk R and disk S after the collision. It must start in the circle, obviously, and point away. If it's 0, right equals 0, and then draw the lengths relative to the scale using figure 2. So like we said, in figure 2 the total was 4, and basically we were told that mv is equal to 4. So let's just start with disk R because it's easier. It tells us that its velocity went from positive 1 to negative 1/2 v. So if it goes from, the velocity becomes negative 1/2 v, we can see that basically the momentum is going to be cut in half because mass stays the same, but velocity is going to be cut in half, so that means the total momentum for disk R is cut in half. So if we initially had 4 tick marks, we're now going to have 2 tick marks. And then also you have to note, it used to be 4 to the right, like they showed us, but since it's the negative, we have to flip it around. So now it's half the amount of tick marks, so 2, half the momentum 2, but it's to the left. Let's just write that, draw that. Start at the center, pointing away, we go 1 and then 2, and then just make an arrow, so add the arrow marks, like that. And you're done with disk R. Then disk S, there are more than one way to solve this. You could try to actually calculate the velocity and actually find what it is in terms of mv and then relate it to that, but relate it to disk R, but that's a lot of work. Another thing you could notice is it's a collision. So, and all basically the collision is like immediate. Immediately after the collision, disk R is moving in the opposite direction. So like they hit and came off. So the impulse is 0, which means the change in momentum is 0. You could just say momentum is conserved. And since initially we can see there was 4 tick marks total. We had 4 here and then 0 here, so the total was 4. Here, the total momentum in the vector diagram still has to be 4. So if we have positive 4, which is important, so here we have negative 2, maybe you wanted to say, oh, I'm going to make it 2 because 2 plus 2 is 4, but no, this is negative 2, so negative 2 plus something has to be equal to 6, 4, which is going to be negative 2 plus 6. So we're just going to draw this S with 6 tick marks and to the right, because the only force on disk S was at rest, and the only force was from disk R from behind, pushing it to the right. So it has to go to the right, even though it doesn't explicitly say so. So we start at the center, and 1, 2, 3, 4, 5, 6. It goes all the way, and then just add the arrow marks. So that is how you do part A. Part B tells us, starting with the conservation of linear momentum. Whenever it tells you to start with something, that's what you have to start, because usually there's going to be one point that is just you write down the conservation of linear momentum. So then it wants us to derive, so make sure to write it down and you start with that one. Don't start with anything else. Even though you might be able to, do not do that. To derive an expression for the kinetic energy of disk S immediately after collision. So disk S, we want its kinetic energy. Express your final answer in terms of m0, v0, and physical constant as appropriate. Begin derivation by writing fundamental physics principle or an equation. It technically tells you that, but initially it told you to start with the conservation of linear momentum, so you follow what it tells you initially. So let's just do that off to the side. I'm just going to do it up here. So we're going to start with the conservation of linear momentum. So P initial equals P final. P final. And we want to find, what do we want to find? We want to find kinetic energy of disk S. So I'm going to put KES using what are we allowed to use? We're allowed to use M0, V0, and physical constants. So use M0, I'm sorry about the handwriting, M0, V0, V0. So first things first, I think, let's just write down our initial moment. Oh, first things first, you have to write this down. That's a whole point. It's a free point, so you should just do it. And then, so initially, our momentum, it was only in disk R. It was the only thing that was moving, this one. And the momentum is mass times volume, as it's in the equation sheet if you forget. So it was just M0, V0. Then after they collide, we had disk R and disk S moving separately, and they both have their own momentum, but we're looking at it as a system. Disk R, disk S system. So we're going to add them. So the momentum of disk R is same mass, M0, times its velocity at the end, which is -1/2. Or let's just do negative V0/2, which is the same thing. And then disk S, what was disk S? Disk S was 3m0. And then they actually never told us its velocity, so we're just going to put our random variable, VB. So that's a good way to start. But then we're trying to find kinetic energy. So what is the kinetic energy equal to? The kinetic energy, I shouldn't put KE because that's not the way College Board does it. So it's only K. So K is equal to, let's put KS because it's of disk S. KS is equal to 1/2 mv squared. So we have mass, it's 3m0, and we're allowed to use that. We need to find velocity, which we put as, I didn't label, ms. We have to find velocity in terms of v0 because we're not allowed to use the variable I made, vs. So we have this equation. Let's just try to solve for vs. So we start just using basic algebra and we just try to simplify it. So, okay, so I went ahead and just did the algebra myself. But if you want a brief explanation, I added m0 v0 over negative m0 v0 over 2. I added that to both sides, and these are like terms, so I get 3/2 m0 v0. And then I just divided the m0's canceled out because there was one on both sides, and I just divided both sides by 3, and I got that vs is equal to 1/2 v0. And so then that's all we need. We have velocity in terms of v0, and they already gave us mass in terms of m0. So then ks is equal to 1/2 3m0. You have to make sure you put the 0 so that they know. And they might take off a point and just put m, since technically you're just naming a random variable for them. And then we said vs is equal to 1/2 v0. So 1/2 v0 squared. And then if you want, it's better to simplify. So we have 1/2, that's 1/4. We have times 3, so 3/4 m0 v0 squared is equal to kinetic energy of disk S after they collide. Okay, so we're done with part B. We'll move on to part C. It tells us that the graph shown in figure 4, which I'll show you guys later, represents the position x as a function of time from t equals 0 until t equals t1 for each of the following: disk R, disk S, and the center of mass. On the graph shown in figure 4, draw the 3 lines that represent the positions x of disk R, disk S, and center of mass from time t equals t1 to t equals 2t1. Distinctively label each line. So basically they gave us the position time graphs of disk R, center of mass, and disk S from t equals 0 to t equals t1. They're asking us, show us the position time graph after they collide. So from t equals t1 until t equals 2t1. So a good thing to notice, which is very important, is this is a position time graph. So the y is the change in x, so change in x, and then the y is changing x, and then the x-axis is time. So we get change in x over time, which tells us that our slope is actually velocity, right? And then we can also remember that momentum is equal to mass times volume, and we know that our mass never changes. So basically, we know that our slope on this graph is directly proportional to our momentums, which we have, right? So like we said, our slope is proportional to our momentums. So the easiest one to start with is center of mass. Center of mass is of the two object system, and we agreed, and I explained before, the momentum does not change. The momentum is constant. So this is just, we're continuing it the same thing. So from t equals 0 to t equals t1, we went up 1 to the right 2, so we're just going to keep the exact same slope. So we're going to start here, up 1 to the right 2, and end at t equals 2 t1. And it's important that you end on this line, because if you end earlier, like if I stopped right here, they wouldn't give me points, because technically I did not show the function until t equals 2t1. Okay, moving on, let's go to disk R. So we know that disk R, its momentum was initially, like I said, or let's just say velocity. Oh yeah, momentum. Its momentum was initially mv. So let's just say its momentum was 1. And then after that, it was negative 1/2. So first thing I know is going to be pointing downwards, because now it's negative and not positive. And then its magnitude of its slope. So let's say this thing is 1. It's going to be 1/2 this. So this was up 4 to the right 2. Now mine's only going to be, instead of 4 over 2, it's going to be 2 over 1 over 1. Yeah. So because this was 4 over 2, now it's going to be 1 to 1 and negative. So we went from here, it's going to be like this. And explaining it again, we know our initial momentum was mv0, which I said is directly proportional to the slope, so it doesn't matter if we can use it, mv0, and then after it was negative 1 over 2 mv0. So it has to be downwards, and it's half the magnitude. The slope is half the magnitude, so the change in y over change in x is going to be half, so we went from 4 over 2, which is 2, to 1 over 1, which is 1. If that makes sense. Disk S, on the other hand, it went from 0, which is why it was a straight line, because the slope is 0. And then it became, like, if you forget, you just go and double check. It became 1 over 2 v0, or 1 over 2 mv0. So we would go from 0, and then our slope would actually become like this. Because remember, we went from 0, and then our final velocity was 1 over 2 v0. And 1 over 2 v0 is the same thing as this one, where we drew for disk R, except that it is positive. An important thing to note, it boldly says label each line. So that is an important part, and it will probably cost you points, because they don't know what you're drawing, because they're all coming from the same point. So this would be, just write S, this would be maybe CM, and then this would be disk R. And that. Moving on to part D. During the collision, the magnitudes of the change in momentum of disk R and disk S are delta momentum R and delta momentum S, respectively. Indicate whether the delta momentum R is greater than, less than, or equal to delta momentum S by writing one of the following. So it's asking us what had a greater change in momentum, disk R or disk S, and we have to do this, and we justify by referencing a fundamental physics principle. Okay, so I paused it for a moment just to get this equation from the equation sheet. So basically this equation is telling us its impulse, so J's impulse, it's equal to force times change in time is equal to the change in momentum. So I'm going to answer right now, and then I'm going to explain why. But our answer is going to be that the change in momentum for disk R and disk S is equal. And so based on this equation, it tells us that the change in momentum is equal to force times change in time. We know that when they collided for the same amount of force. And since they were both hitting each other, based on Newton's third law, there was an equal and opposite reaction on both. So the force was the same, the change in time was the same, because it was just the time that they were touching each other. So that would mean that the change in momentum would be the same, and you would justify it using this equation. So that would look something like, Only force between each disk. So it looks something like this. The change in momentum for disk R is equal to the change in momentum in disk S, which is based on the impulse change in momentum equation, this one, which states that the change in momentum is equal to force times time. The only force was the collision between them, which exerted an equal and opposite force on each disk, and the time was equal since it's the time the two disks were in contact, making the change in momentum the same for both disks. And that's how you would go about answering part D, which is the last part. So that is it for FRQ number 2 of AP Physics, AP Physics 1 2026 FRQ. And I've probably uploaded the rest by the time you see this. So if you want, go ahead and see those. And thank you for watching.